Hello everybody, welcome back to the Gregorius Maths video. In this video, we're going to be starting looking at some homological algebra. And one of the most fundamental objects in homological algebra are chain complexes. Okay, so, what is a chain complex? Well, a chain complex is a sequence of, let's just say modules, let's just drop that. Modules, Cn, let's just do it like this. So we have maps, so Cn plus 1, and then this goes via dn plus 1 to Cn, and then this goes via dn to Cn minus 1, so forth, such that dn composed with dn plus 1 equals 0. And this condition right here is equivalent to saying that the image of dn plus 1 is a subset of the kernel of dn. Therefore, this right here it turns out to be a normal subgroup of the kernel, and so we can use quotient groups to measure the exactness of this. That is, it's exact if the image is equal to the kernel. And so to do this we use homology. So we'll use a different colour to do this. The nth homology of this chain complex, which we can denote like this, is, and then we're going to have Hn of the complex is equal to the kernel mod the image, dn mod the image. So clearly when this is trivial, that means that the image is equal to the kernel and it's exact at that point. Now, similarly, we have the notion of a cochain complex. A cochain complex is a sequence of modules, blah blah blah, blah blah blah, blah, and then this goes to Cn minus 1, and then it's actually going to go up. So the differential, so we're going to be increasing rather than decreasing. See, in this one, the dn plus 1 maps from Cn plus 1 to Cn, whereas this one goes from Cn minus 1 to Cn. So forth. And again, such that dn composed with dn plus 1 equals 0. And again, this is equivalent to saying that the image of dn plus 1 is a subset of the kernel of dn. Oh, sorry, I saw this minus and thought it was a plus. Such that sorry, apologies. So let's just use this. Okay, so dn minus 1 composed with dn. Sorry, dn composed with dn minus 1. There we go. It's equal to 0. And then we're just gonna. This is equivalent to saying dn plus 1. And then the image of dn is a subset of the kernel of dn plus 1. Apologies for that. Anyhow, again, we can measure the exactness with the nth cohomology. let's use blue for this. The nth cohomology is defined as Hn of this complex is equal to the kernel of Dn plus 1 mod the image of Dn. Now, the homology of a complex is defined as just the direct sum of all of the homology groups, and the cohomology is defined as the direct sum of all the cohomology groups. I didn't write that down, but you know what. So, now a natural thing to ask is, are there maps between chain complexes? And if so, do they induce maps between the homologies of chain complexes? So, we're just going to study cochain complexes, but the definitions are all analogous for chain complexes. So, a cochain map F between two chain complexes is actually a sequence. Fn, which takes you from Cn to Dn, such that, and now we're going to have a commutative square, so at the top right we're going to have Cn mapping via the differential on C to Cn plus 1, and it's going to go down via Fn to Dn. Now Dn is going to go via the differential Dn d to Dn plus 1, and now this right here is going to map via Fn plus 1 to Dn plus 1, such that this commutes. What precisely does this mean? Well, this means that if we go jum, jum, that's the same as going jum, jum. In other words, dn, d, so the differential on d, the nth differential on d composed with fn is equal to the fn plus 1 composed with the nth differential on c. Now, before we look at the maps that these maps induce, we're actually going to look at a more specific cochain map. So, let's just go in green. Two cochain, again this is analogous for chain maps. Two cochain maps are chain homotopic. If there are a series of maps Hn, which takes you from Cn, two cochain maps. Okay, so we're just going to have F and G from some chain complex C to D, chain homotopic, and it takes you from Cn to Dn minus 1 of maps there, such that now we're going to have Fn minus Gn equals the n minus 1th differential on D composed with Hn plus Hn plus 1 composed with the nth differential on C. Okay? So, now that we have this, we're going to look at the maps that this induces and that And this is an equivalence relation, and one more thing. So, given a chain map, F between two cochain complexes, it induces a map Hn of F, and this takes you from the nth cohomologies of each map, and what it does is it maps the coset, this equivalence class is going to map to the equivalence class of the nth map, so in this sequence right here of C. It's going to map this equivalence class to equivalence class. And actually something that follows very simply is that if two maps F and G are chain homotopic, that chain homotopic, then they induce the same map in cohomology. And the reason for this is well, okay, pick a cycle. So an element of the kernel is called a cycle. So pick a cycle C. Okay? Then we have that Hn of F applied to C is equal to the equivalence class of this, and this is actually equal to, now what are we going to have? Well, look at, where's the condition for it? Look at this condition right here. I might box this in case I need to refer to it later. Look at this condition right here. If we add Gn to both sides, we're going to get Gn applied to C plus, now we're going to have dn minus 1 d composed with hn of C plus hn plus 1 composed with dn, the differential in C, applied to C. Now this right here is going to give you the equivalence class of Gn of C, which is of course equal to Hn G C. But why is this quality right here true? Well, this right here is going to stay, and this right here is precisely in the image of it's in the image, right, because of this right here, and so it just vanishes when you apply its equivalence class to it, because if it's in the image, then its equivalence class vanishes, because it's a quotient of the image, so that's how it works. And this right here, because C is a cycle, this right here by definition is equal to 0. And so that means that the only thing that remains is going to be this. Now, obviously an important thing to note is that that two chain homotopic maps are actually, that chain homotopy is an equivalence relation. So, lemma. Chain homotopy is an equivalence relation. Alright, proof. So what's the proof of this statement right here? Well, reflexivity and symmetry follow easily, but F is chain homotopic to itself via H equals 0. If F is chain homotopic to G via H, G is chain homotopic to F via negative H. The only difficult part is transitivity. So, if F is chain homotopic to G via H, and G is homotopic to, let's just say, K via H prime. Actually, let's use tilde. Then Fn minus k to the n is equal to, and now what we're going to do is we're going to insert gn minus g to the n minus g to the n. And what's that going to do? Sorry, we're going to actually have a minus sign here. Plus g to the n minus k to the n. Well, would you look at that? Because F is chain homotopic to G, this right here can be expressed in terms of like this. And again, because G is chain homotopic to K, this right here can be expressed like that. So we're going to get d n minus 1 d composed with h n plus hn plus 1 composed with dn c, and then we're going to have plus d n minus 1, so the n minus 1 differential in d composed with h tilde n plus h tilde n plus 1 composed with the nth differential in c. And this right here is equal to dn minus 1 d compose, and then we're going to have hn plus hn tilde, and then we're going to have plus hn plus 1 plus h tilde n plus 1 compose dnc. And so actually they're chain homotopic via the map h plus h tilde. And I feel like I was planning to do one more proof, but I don't remember what it was going to be of, so that's it for today. And yeah, I should be going on with homological algebra for a while, and then I might do algebraic geometry after this series. Anyway, thank you for watching, and goodbye!